Let us get started with this theorem. So, in the last module we learnt that if you have a set of vectors that are mutually orthogonal, then they are linearly independent, but it is not the other way around. And using this property, let us see how we can express a vector in terms of its coordinates using an orthonormal set. Let V1, V2 so on till Vn be a basis for an inner product space V. Okay, there is an inner product space V, and let V1, V2 so on till Vn be a basis for this. So, the statement of this theorem is as follows. All of these theorems are really not very hard, they are just easy theorems. If the basis set V1, V2 so on till Vn is orthogonal, then for any x belonging to this space V, you can write this vector x as x with V1, take the inner product, divided by the normalization value for V1 in the direction of V1 plus the projection of x upon V2 divided by the inner product of V2 with V2 in the direction of V2 plus so on till the projection of x with Vn divided by the norm of Vn in the direction of Vn, the product of Vn with Vn in the direction of Vn, right. And if V1, V2 so on till Vn are orthonormal, that is their norm is 1. So, this inner product essentially is basically, right, it is the square of the length, and the length is basically 1, square of the length is 1. So, therefore, all of this is 1. So, basically you can write x in a simple form So, it is basically take the projections or take the inner product of this vector x with all of these other orthonormal vectors, and that gives you the scalar component, and then you take the linear combination of these inner products along the direction of these individual vectors, right. So, this is the theorem. The proof is pretty straightforward, but I think before we proceed with the proof, I think what you have to understand is a sort of an intuitive feel for this representation. Now, what is happening here is exactly like what we thought about in the representation of vectors, right. That means we take the projection of the vector in the to the each of the bases and then that gives you basically the amount of the length that you have to consider in the direction of the basis. So, for example, if you think about 2I plus 3j, right, if you think about 2I plus 3j, which means your two units in the I direction and 3 units in the j direction, and these inner products are essentially those units in that direction, right. So, this is the basic idea. And now once you think about this in terms of vectors, it is probably not too difficult to imagine these in terms of functions, right. So, the function, an arbitrary function, can be written as a linear combination of some functions, and this is basically a linear combination of these basis functions, and you have to figure out what is the amount of what weightage do you give to that particular basis, right, and that is basically the amount of the length in some measure, right, in terms of the inner product of that function with the basis or that vector with the basis. So, throughout this, as we think about vectors, we have to also think about in terms of signals as well, and we will see that they are linked with each other, and that is what we will do. So, the proof is very straightforward, very easy proof. So, what we do is we write x in terms of some components that connect the basis, right. So, a vector x can be written as x1 in the direction of v1 plus x2 in the direction of v2 plus so on till xn in the direction of vn, right, and this is because basis, it is a basis, therefore, they are linearly independent. Now, the trick is just take this vector x and look at its inner product with each of these vi, right. So, x with vi is basically xi with the inner product of vi with vi, right, because vi with vj will just vanish off because of orthogonality, right. So, therefore, we can write x in this form, which is summa. I will say this is because of orthogonality, I equals 1 to n. So, now I want to express xi using this equation that I have. This is basically the inner product of x with vi, inner product of vi with vi, and then in the direction of vi. Now, this can be more compactly written in this form, I equals 1 to n x with vi in the direction of vi if they are orthonormal, that is vi dot vi is 1 and vi dot vj is basically 0. I mean, of course, we assume that here and then we just normalized it, and this is pretty straightforward. So, what we have done now, we have taken a vector and in terms of a orthonormal basis we have expressed this vector, and we can exactly compute what the coordinates or okay. So, it is pretty straightforward result. I think what is very important, I sometimes even wonder how Descartes imagined this orthogonality, orthonormality idea through this coordinate geometry. I mean, you see a lot of advancement as you think in very formal terms when you think about linear algebraic framework, but when you think about really some of these very early mathematicians, and this sense of intuition is something that you should have to be able to kind of realize how to construct things. So, I mean, if you are told in your 5th grade or 6th grade that this is the reason why, perhaps you have to consider the Cartesian plane, maybe x y being mutually perpendicular, right, mutually perpendicular axis. So, if you were taught this theorem, definitely you would find graphs very hard to even plot a function, right. But I think if you now you can really appreciate the connections between orthogonality, linear independence, and then basically writing this in terms of coordinates. So, with this theorem, we will now proceed to an important step called the Gram-Schmidt orthogonalization. So, what is the motivation for this procedure, right? So, I am given a bunch of signals and I want an orthogonal basis to represent the signal in terms of the basis signals or basis functions. Or going back, I give you a bunch of vectors and I want to get a basis to represent any vector in this set, right. Some of them could be linearly dependent, some of them may not be linearly dependent, but those that are linearly dependent, somehow I want to figure out to express them in terms of a basis. So, with this motivation, we develop this notion of Gram-Schmidt orthogonalization procedure, which is very useful to basically construct an orthogonal basis for a vector space or an orthogonal basis for a signal space. Okay. So, the motivation is construction of an orthogonal basis for a vector space or possibly an orthogonal basis for a signal space. So, let us suppose we are given vectors x1, x2 dot xn. So, here is a procedure what we could do and where we could start actually towards getting an orthogonal basis for V. So, let us start with this vector. Let V1 be this vector basically be x1. I will talk about normalization later on, but let us just think about orthogonality and get this intuition, and then we think about this more rigorously. So, V1, this vector is basically x1. So, I give you one vector, right. What is the basis for that vector? itself, right, there is nothing more. So, therefore, I can say V1 is x1. Now, V2 is, I am given another vector from this set, from this pool. I pick up this vector x2, then I project x2 in the direction, I project x2 with V1 in the direction of V1. So, what exactly is happening here is basically I am removing that component of the, I am removing that component of the vector in x2 in the direction of V1. So, think about this intuition, I have I, j, k mutually orthogonal. If I want to get the direction of k, I want to remove that in the direction of I. I want to remove that in the direction of j. So, I basically have to remove all these pi's to get what I really want, right. So, that is the very simple idea behind this construction, and let us see how this works, right. So, then I go with V3, this is x3 minus, take x3, take the inner product, take x3, take the inner product of x3 with V1 and remove that component, take x3 with V2 normalize it, remove this in this in the direction of V2, so on, right. And if you do this for Vn, you have xn minus summa I equals 1 to n minus 1 xn minus xn with Vi, take the inner product of xn with Vi, Vi with Vi in the direction of Vi, right. So, remove all the n minus 1 components in their respective directions, and that is what you have, right. So, the claim is the set Vi I equals 1 to n forms an orthogonal basis for this vector space V, and if we normalize, it forms an orthonormal set. Right, if we normalize this, it forms an orthonormal set. So, I will leave this proof as an exercise. So, the idea is straightforward. I already gave you the idea. You can try this with straightforward algebraic proof to work this out, else try alternative methods such as induction logic to show that this procedure is correct. But before we sort of wrap this, just get a picture of why this should work, right. I mean, if you just even just routinely work through the algebra, take the inner product of V2 with V1, right. So, you have x2 with V1 minus this thing, right, and then V1 with V2 with so V2 with V1. So, V1 with V2 is basically you want it to be 0, it is going to vanish there, right. And then so you will have V1 with so V2 with V1, so is x2 with V1 minus this component V1 with V1. So, V1 with V1 this would cancel, you will have x2 with V1, x2 with V1, and which is basically 0, right, which is straightforward to think through. So, I will leave this proof to you. So, the idea is as follows: I give you I, j, k, so on, that are all mutually orthogonal if to start with. So, the idea is if I want k, I have to remove I and j, and if I have I and j together and I do not want I have to remove that component in the direction of I, and that exactly is the idea here, right. So, the proof is very straightforward. I will leave this as an exercise, homework exercise. The solutions would be supplied. So, prove this claim by any of your favorite methods. So, we will just revisit an example just for the sake of a numerical exercise. So, consider the following vectors in R2, just 2-dimensional vectors. So, I have 3 2 is one of them, 4 1 is another. So, if you want to get an orthonormal set, we just follow the Gram-Schmidt orthogonalization idea. So, we basically start with V1, V1 is my x1. Let us do just the orthogonality and then we will normalize later, right. We start with this vector which is 3 2, and V2 is basically x2 minus the inner product of x2 with V1 upon the inner product of V1 with V1 in the direction of V1. So, if you just work out the numerics, this is vector 4 1 minus, if you work out this math, it just happens to be 14 upon 13 times the vector 3 2, and you can just verify that V1 with V2 is 0 just for the sake of it, and you will land up with the basis E1 is 1 upon root 13 times this vector 3 2, and you have a root 13 here because you have to normalize this so that this vector is of length, this E1 is normalized, right. So, therefore, it is 3 square is 9, 2 square is 4, 9 plus 4 is 13, and that is where you have this root 13 factor, and E2 is similarly 1 upon this vector is 10 upon 13 and minus 15 upon 13. You just have to take the sum of the squares of these two components. Okay. So, this is basically completion of the Gram-Schmidt orthogonalization procedure. So, this is a very important step because at this stage, given a set of vectors that are possibly linearly dependent, we can through construction come up with an orthogonal or an orthonormal basis for this collection, such that any vector in this collection can be expressed in terms of this orthogonal set or this orthonormal set, right. And orthonormal set is very important because we can get the coordinate representation of the vector. Clear? So, with this in mind, we can start off with a signal processing exercise, and we have all the background now from our linear algebra and vector spaces.